Hi, I'm Roger Pertwee, and I'm Emeritus Professor here at Aberdeen University in Scotland, where for many years I've been working on cannabinoids, particularly on the pharmacology and therapeutic potential of cannabinoids. It's a great pleasure for me to be here today for Professionally Cannabis.
Where do they go, the smoke rings I blow each night?
It is an honour and a privilege to welcome to the pod a friend and, more importantly, legitimately one of the pioneers of cannabinoid pharmacology research, Professor Roger Pertwee of the University of Aberdeen. With 3 degrees from Oxford, a Lifetime Achievement Award for spending over 50 years in cannabis research, and a friendship with Dr. Raphael Mechoulam that dates back to their early scientific breakthroughs, Roger is, in no uncertain terms, a true legend and someone who I intend to hang off every word. With all this in mind, there's only one thing left to say. Roger, welcome to the Professionally Cannabis Podcast.
Thank you very much for inviting me. It's a great pleasure.
We're very happy to have you with us. And wow, I didn't realise you had 3 degrees from Oxford. I guess you could never get enough. But anyway, what I'd love to ask is what led you to the plant?
Oh, well, what happened was I was doing a degree at Oxford in biochemistry, and during that time as an undergraduate, I had the opportunity to work as an officer cadet with the Army, with the Royal Engineers, and I became, in fact, a qualified shallow water diver. And one thing I learned during that course was about a thing called inert gas narcosis, or how air at high pressure, if you breathe it at high pressure, which you have to do if you dive down deep, can make you feel drunk. So I found that a very interesting idea. And so I looked around in Oxford for anyone with whom I could do a PhD on that, or DPhil, as they say in Oxford. And I found someone called Professor Peyton, who's the professor of pharmacology there, and he took me on. I was lucky enough; he took me on for an MRC-funded DPhil project on that. So I spent 3 years on that. At the end of that, he was mainly an anesthetics expert, but he was interested in the possibility that maybe cannabinoids act a bit like anesthetics, and so he managed to get some funding to study that and took me on as a postdoc to work on that. And that, of course, was at a time when shortly after the THC had been identified by Raphael Mechoulam in the so this was talking about the 1960s here, the middle late 1960s and early 1970s. So that's how I got into cannabinoids, and it was at a very interesting time, in fact, when cannabis was becoming increasingly used recreationally. There was then, of course, still a medicine, a cannabis-based medicine actually around called tincture of cannabis. It was a dark green liquid. My wife, who was a nurse, we used to give it to patients. It was a legal medicine for pain relief. But then it got banned because the government was worried about that it might be used recreationally. But we used it. We used to buy it for the lab, and it was from there that we extracted the cannabinoids that we studied.
And wow, there's lots to unpack there. So you got into it through scuba diving, already incredible. So I kind of want to ask, one, is that intoxication that you get from the high air pressure related to cannabinoids at all? Or was it just sort of general intoxication that brought you there? And 2, this old cannabis medicine that you had access to, is that similar to the oils that patients are getting today?
So the feeling of drunkenness you get is, there's no evidence really that it's acting through cannabinoid receptors. The air at high pressure, the nitrogen in the air at high pressure is probably not acting through those receptors. But interestingly, cannabinoids do share the ability of anesthetics to affect the fluidity of membranes of cells. So there may be some overlap. But of course, the main effects of cannabinoids like THC involve actions acting through receptors, cannabinoid receptors, and there's no evidence that the anesthetics do that. As to the dark green liquid, tincture of cannabis, that's quite different, I think, from drugs which are sold in shops these days, cannabinoids. It's a dark green liquid. It's made up of alcohol, and the cannabinoid material is dissolved in that alcohol. It's this dark green liquid.
So perhaps similar to some of the tinctures that would be made through ethanol extraction. And I ask because rather than, say, highly specific molecules like your, marinol or dronabinol, there seems to be, at least in Germany and in North America, a sort of return to a more, I don't know what to call it, a less specific cannabinoid medicine that is just either extracting through a CO2 or an ethanol extract, something that gives a full spectrum oil. Those are even available in the UK now, I believe.
Yes, that's right. So the tincture of cannabis was a mixture of lots and lots and lots of different cannabinoids, which is why we got it, because we were able to extract some of those. And it was actually in tincture of cannabis that we discovered one of the plant cannabinoids. We were the first to discover it, actually, called THCV, or tetrahydrocannabivarin, which is structurally similar to THC, but not the same structure. And in fact, instead of activating cannabinoid receptors, CB1 receptors, it blocks the CB1 receptor.
So with a lot of this research that you've been focused on starting in the 60s, something that I'm really keen to understand, Roger, is there or was there a point in time where the research that you were doing became harder because of socio-political activity that was going on? Obviously, lots of it led from the United States.
Not that I know of, because when I started, of course, it was my boss who organised all the regulatory things. And then when I moved to Aberdeen here in Scotland in 1974 to take up a lectureship, I started having to do that. And of course, to work with cannabinoids, you did need a license from the Home Office, and you had to renew that every so often, and still do. That's still the situation, and it's something I do. Apart from that, there weren't really any problems, and in fact, it got increasingly easier as cannabinoids became available commercially, so you didn't have to extract from the plant anymore.
Can you give us a little crash course over the shape, or not the shape, but perhaps the focuses of your research over time, because you've had such a long career in this game. Presumably what you're looking at nowadays is very different from what you were looking at 30, 40 years ago.
Well, initially we were studying the pharmacology, and I did do pharmacology and became, I did my first degree in biochemistry, but I really became a pharmacologist. And initially we were looking to explore the effects of drugs like THC, tetrahydrocannabinol, which is the main psychoactive constituent of cannabis, and 1 or 2 other plant constituents like cannabidiol and THCV, as I mentioned earlier. And really very little been done to produce assays to measure the effects of those compounds in the laboratory. And so one of the things I was doing to start with was to develop such assays, and they came up with one, for example, called the ring test for THC, where you place a mouse across a ring, a metal ring, and you see how long over a 5-minute period it remains immobile. And it was interesting. It would go off into a trance-like state. It retained its grip, so it would maybe hang by 1 or 2, 4 legs from the ring, or rest across the ring in an immobile state. And the bigger the dose, the longer it did that. And that became one of 4 tests what's called the tetrad test. And what was interesting was that drugs with THC-like properties seem to have equal potency in all 4 of the tetrad tests, the other ones being hypothermia, that's a ability of cannabinoids to lower temperature. That's another thing, body temperature, that's another thing I studied. And in fact, we obtained very good evidence that in mice at least, what THC did, the main psychoactive constituent, what it did was to lower the thermoregulatory set point so that the animal regulated its body temperature still, but at a lower level than normal, the opposite of fever, if you like. So it might drop its temperature down 3 or 4 degrees and then regulate it at that lower temperature. And I developed one assay for that, which was one in which the animal could shuttle between warm and cold environment in a ring, sort of a tunnel, ring-like tunnel, half of which was warm and half of which was cold. We gave it THC and it rushed into the cold. Its temperature went down, and then it would shuttle between the warm and the cold to keep its temperature at that lower level. As far as the tetrad test is concerned, the other ones were motor function and also analgesia. Another one was cannabidiol, which is a very well-known plant cannabinoid, which is not psychoactive. And we also studied it and showed, in fact, how, for example, it affected functioning in the liver, and it targets certain enzymes in the liver, which is an interesting action. But in those days, it was so little known. There were so many things that one could do, and that was how it went. When I moved to Aberdeen, I found out that one of my colleagues there, who just retired, a well-known professor of pharmacology there, Professor Kostelitz, he and his group were studying opioids and discovered endogenous opioids called endorphins or enkephalins. And to part of their work involved using an assay called the mouse isolated vas deferens assay, in which you take the vas deferens from a male mouse and put it into an organ bath and study the effects of drugs on that. And I had the opportunity to try that out for cannabinoids, and amazingly, it turned out to be a really good assay for cannabinoids as well. Subsequently, shortly after I did that, the cannabinoid receptors were discovered. So what was discovered was that our bodies and animal bodies contain at least 2 cannabinoid receptors. First one to be discovered was the CB1 receptor, CB1 cannabinoid receptor, which is present on the loss of neurons. It's one of the most highly expressed receptors in the brain, actually. And what it does when it's activated very often is to reduce the release of transmitters from nerve terminals, and so reduce synaptic transmission. And the other receptor was the CB2 cannabinoid receptor. That is found a lot on immune cells, and so it has quite different functioning. But the discovery of those receptors really prompted the question, why do we have those receptors in our bodies? Is it to get high in cannabis as far as CB1 is concerned? Clearly not. There must be some other reason why we developed them. And that led to a search for compounds produced in our own bodies which can target those receptors. And that led to the discovery of what we call endocannabinoids, that is endogenous cannabinoids, which are produced by our own bodies and also by animals, of course, as well. And that research was led by Raphael Mechoulam in Israel, but I was lucky enough to be involved in it because it was the vas deferens that we used to show that anandamide behaves like THC.
And with regards to the work that you have done with Raphael Mechoulam and other leading cannabis researchers in the early days of cannabis research itself, could you talk a little bit to how, I guess, information and research between different research organizations used to be shared? And perhaps could you also talk to the types of and ways in which you would collaborate with folks like Raphael Mechoulam in the early days?
Well, what happened was, of course, this was indeed in the early days, initially without any emailing, so it was all done by letter and so on. But initially, very often, one would meet up with other scientists at conferences. And that was very important. And it was indeed at conferences that I first met, Raphael Mechoulam. And but he was also aware of my work because he knew about my boss in Oxford, Professor Peyton. And in fact, he put together a fantastic book on marijuana and its pharmacology and potential therapeutic uses, but everything about it that was known in the early 1970s. And he asked us to write a chapter, in fact, a couple of chapters in that book, which we did. Strangely enough, that was at a time when there were problems with power in the UK, the power cuts day and night because of strikes. And in fact, Professor Peyton and I used to work in the evenings on this in his office. And we had to work by candlelight very often because there was no electricity. And of course, we had to write everything out in longhand because there was no computers in those days to type things out on. So then we used to give the written versions to a secretary who would type it all out. It was quite different in those days.
I assume you're no longer working with candlelight right now. So
sunlight.
sunlight. far more sustainable. I guess the world has changed. So what are you looking at with your sustainable eyes now? What's the modern problems you're investigating now that we've done sort of the early basic work? Although I would say that the thermoregulation properties are not widely discussed or used. But anyway, that's an aside.
Well, it would be very interesting to know whether that thermoregulation effect extends to humans, because we did the work in animals, but that would be perhaps very interesting to study. Interestingly, there was a recent report, both in a paper and also in the news by the press, that there's a lady near here in Inverness, and she produces endocannabinoids like we all do, but she has about twice the normal amount of anandamide, the first of the endocannabinoids to be discovered, about twice the normal amounts of that in her body and in her blood, and that's because she can't metabolize it very well, so it builds up in the body much more than usual. And she says she feels very happy-go-lucky as a result, so it's boosted her mood, etc. And also she doesn't feel much pain. So
I remember hearing about this. Yes. She has trouble sort of feeling, if someone was to pinch her, or if there was heat on her arm or something, sort of wouldn't pick it up in the same way that you or I would. That's right.
That's right. And in fact, pain can actually be quite useful to us in a way, protective, because she, for example, sometimes smells burning meat in her kitchen, and it's actually her burning. She's put her hand on the stove or something, and she's burning, and she doesn't know, she doesn't feel it. So pain is protective to some extent, but of course it can also be very nasty when it's being produced by various disorders.
Very interesting. So is that a topic that you're looking at now, rather than cannabinoids, endocannabinoids, and how they work?
Well, no, it's something I think we should explore more. It'd be interesting to know how many people are like that lady. And that could be really interesting. But one of the things I've been exploring involves a part of the cannabinoid CB1 receptor called the allosteric site on that receptor. And what we have on receptors like cannabinoid receptors is an orthosteric site. So you have a drug which can activate the receptor normally, it acts on the orthosteric site to produce an effect, for example, pain relief or whatever. But on some receptors, including we discovered on the cannabinoid CB1 receptor, there are allosteric sites. And if you target those with a ligand that's active, then you can modulate the extent to which the orthosteric site can be targeted. So you can either increase or reduce the ability of an orthosteric agonist like THC or an anandamide to activate the orthosteric receptor. And as a result, you can turn up or turn down the volume, if you like, of the receptor effects in the body. And that's very interesting therapeutically, I think, although it's yet to be explored in the clinic. But certainly preclinical studies have shown, some conducted by collaborators of mine, who also produced some of these allosteric modulators. What we found was that certainly they can reduce pain, reduce analgesia in animals, in a way that does not involve the production of tolerance or dependence. What they're doing is strengthening the activation of the receptor by endocannabinoids, presumably, because by themselves they don't have any effect. They need an agonist there, a drug which can directly activate the orthosteric site, to be there as well. And so that's an interesting one. Another one, discovery, again made by collaborators with one of these compounds, is that if you give one of these compounds to animals, you can lower the pressure in the eye in a way which would reduce the problems of glaucoma, where you get an excessive build-up of pressure in the eye.
And Roger, as someone who has done so much work in the sort of preclinical sphere, could you sort of talk us through the steps in which sort of a research organization would need to go through, or the results that preclinical studies would have to produce to open that pathway through to the research moving on to clinical studies? And has the way in which studies evolve from preclinical to clinical changed over your long career in research?
Well, an interesting experience for me really was in the early 1990s when, reading newspapers, I noticed that there was a lady journalist, writing about how cannabis she had multiple sclerosis, in fact had to stop being a journalist because of that disorder. But she still would write articles about this particular subject. And she used to self-medicate with cannabis because she said it reduced the spasticity and pain of multiple sclerosis for her. I managed to get hold of her, difficult in those days before email, but I managed to do that, to talk with her. And it turned out she was part of a group of patients, both in the UK and in the USA, who were self-medicating with cannabis. And so through her, it was possible for me and some colleagues to contact those patients and to send out a questionnaire to each of them, which they returned directly to us. And then we wrote up what they claimed in a publication. And basically what they all seemed to claim, they were pretty, as we had pretty similar claims from different people. It was the cannabis, they took it because it was good in reducing the pain of the multiple sclerosis, the spasticity of the multiple sclerosis, and also this helped with their sleep as well, which is why they took it. That evidence was also looked at following on from our publication, by the British Medical Association, and also featured in a House of Lords report, and I contributed to both of those, and to one or two other reports as well. And at the end of it all, cannabis did appear or cannabinoids did appear as treatments for multiple sclerosis, and they became approved medicines. And it was actually a company called GW Pharmaceuticals which came up with the first such medicine called Sativex, which contains equal amounts of THC and cannabidiol. And what happens is the patients take it as an oromucosal spray. It's in alcohol. They spray it into the mouth, and the idea is to absorb it from the mouth. That's probably the best way to go, because it goes from the mouth directly to the heart and then it's distributed in the body. If you swallow a medicine, then very often when it's absorbed into the body from the gut, it goes first to the liver, which may not be a good thing for drugs like cannabidiol. But being absorbed from the mouth is quite good. And certainly they did clinical trials and it worked well, and it became an approved medicine, and is still an approved medicine. And it was actually after that I collaborated with a group in London who led some research on preclinical research. So in this case, everything was back to front. We started with the patients, then there was clinical trials carried out, and finally preclinical scientific research was carried out. But that research also supported the idea that cannabinoids like THC and cannabidiol will be good for treating multiple sclerosis. There was another very interesting story, really, which concerns epilepsy. What was happening was that apparently there are a lot of, or a significant number of young children who have epilepsy, which can't be treated with normal approved drugs. And there was, for example, a lady who appeared in the press about this, and her son, a very young son, regularly had fits, had seizures, epileptic seizures, and would wake up screaming in the night and would wake her up. And she actually got some cannabis from the Netherlands and gave it to her son, and found it really worked well in reducing the number of seizures. And that appeared in the press. And I think that might have prompted GW Pharmaceuticals to develop a cannabidiol-based medicine called Epidiolex for treating that kind of epilepsy. For example, Dravet syndrome, which is one of those kinds of epilepsies which are difficult to treat with most anti-convulsant drugs. So that appeared, and that's now an approved medicine as well. But the starting point there, again, were patients.
As someone that has done a lot of work with plant-derived cannabinoids and then also synthetic cannabinoids, what's your experience with this? What are the sort of core differences you found with using plant-based cannabinoids and synthetic cannabinoids? And perhaps as an extension of that, are there any results that you have previously found in research of yours, either using plant-based or synthetic, that might not be mirrored in the same way if you were to use the other derivation of the cannabinoid?
Oh, that's a very interesting question. But the answer is no. I haven't really. It was more. We didn't do them in parallel. It was the initial work in Oxford, where very little was known anyway, where we were using the plant-derived cannabinoids, and then subsequently it was synthetic cannabinoids that I was really mainly using in my laboratory.
With regard to the array of cannabinoids that could have therapeutic benefits for people and use within medicines, are there any particular cannabinoids that you've come across that we haven't covered yet in today's conversation that you think would definitely benefit from more research being done from them, or early signs that this cannabinoid could have exceedingly useful therapeutic properties?
Sure. So we mentioned THC and cannabidiol. Another one is cannabidiolic acid, which is a precursor of cannabidiol in cannabis, and it actually has very interesting properties because it's like cannabidiol. It produces signs of reduced anxiety, for example, but it seems to do so to better than cannabidiol. For example, it's more potent than cannabidiol, and it's got cannabidiol for anxiety relief. It's got what's called a bell-shaped dose response curve, which means it doesn't work at very low doses, nor does it work, though, at very high doses, but only at intermediate doses. And the cannabidiolic acid's got a broader bell shape, so it acts over a broader range of doses. One problem, though, with cannabidiolic acid, it's not very stable. And that actually prompted the development of a synthetic analog of it, which has got the carboxyl group on the cannabidiolic acid is methylated to form this new compound, and that works even better than cannabidiolic acid in animal models of anxiety, and also in animal models of chemotherapy-induced nausea and vomiting, in which the drug reduces signs of nausea and vomiting. And that medicine was, that new compound was actually designed and synthesized by Raphael Mechoulam, again, with whom we were collaborating on that. We were also collaborating with a group in Canada who were doing in vivo work with those compounds, that is with the synthetic analog and also with cannabidiolic acid and with cannabidiol. Another example of a cannabinoid with therapeutic potential that I've looked at is one called cannabigerol. And cannabigerol, interesting in that it seems to produce signs of pain relief, very good signs of pain relief, but not by acting through cannabinoid receptors, but by acting through adrenoreceptors, alpha-2 adrenoreceptors, receptors for noradrenaline in the brain.
I think we've probably got time for one or two more questions. So I guess I'll take it to one question, and I'll give you something sort of a bit of a retrospective. And this is, what are you most proud of in terms of discovery or pharmacology that you've worked on so far in terms of your research that you provided to the world? Or what is the thing that you're most looking forward to discovering?
I think probably one of the most exciting things was discovery of the allosteric site on the cannabinoid CB1 receptor, which created, which is really a very exciting potential target for new medicines. The other one was being involved in the discovery of the endocannabinoids with Raphael Mechoulam, which really, as I say, depended on me having developed a new assay for cannabinoids, including THC at that time. That was at a time when the receptors had been discovered, but there were no antagonists around to use as pharmacological tools to see whether anandamide was acting on the receptor or not. So what I did instead, and that again was quite exciting, was to, because we used to take the vas deferens from mice, so I made the mice tolerant to THC before taking out the vas deferens, and then showed that the vas deferens was also tolerant to THC and also tolerant to anandamide. And that really confirmed that that the anandamide was acting on the receptor, on the cannabinoid receptor, because of that tolerance effect. Subsequently, we were able to show when a CB1 antagonist came along, a blocking drug came along, that it did block the effects of anandamide. Since then, an allosteric site was also discovered on the CB2 receptor, not by us, but by another group. And I've been collaborating with a medicinal chemist in Italy, actually, to develop CB2 allosteric modulators as well. Interestingly, in collaboration with a group here in Aberdeen, using one of these compounds produced by the Italians, we obtained good evidence that it might be good for treating certain kinds of cancer. So that's another potential way forward. Of course, there's two kinds of allosteric modulator, positive and negative. Positive turn everything up, and negative turn things down. And in fact, the CB1 receptor, cannabidiol, is a negative allosteric modulator. There's good evidence for that.
Fascinating. Well, I think that's all we've got time for today, but you've given us and our listeners a lot to think on. So from myself and Jonathan, I just want to say thank you very much for joining us today, Roger.
Oh, thanks for asking me.
Please take me above, take me with you.